Well, everything about Apollo was brand new in terms of the technology. They had only been flying in space for a very short period of time when we announced that we were going to go to the moon. We had basic rockets that could do some activities in space in low Earth orbit, but we certainly didn't have a vehicle that could go all the way to the moon. So we had to build that from scratch. The Saturn V becomes the rocket that the astronauts flew to the moon, the most powerful rocket ever built. And it worked beautifully, but it took almost 10 years for that technology to mature to the extent that they could actually use it. So that's the first type of technology, the rocket technology. And it wasn't just the size of the rocket, it was also the engines. Rocket engines are all about how much thrust you can produce. And nobody had produced anything like the F1 engine that was at the base of the Saturn V. 1.5 million pounds per engine, with 5 of them at the bottom of that rocket. So 7.5 million pounds of thrust. Very big engines. The second piece of technology was a capsule that could sustain the astronauts all the way to the moon and back. So for a couple of weeks in deep space. That was a tall order. We'd never done anything like that before either. We understood a little bit about how to build a spacecraft that could sustain humans, but those trips in Earth orbit at that point were very short. They were very simple. And oh, by the way, if there was any problem, you simply hit the retros and they come home. So it's not the type of risky technology that they would have on Apollo. And again, those worked relatively well during the flights to the moon, with the exception of the Apollo 13 mission where they had an accident. They brought him home alive, but it was a tough process. And then finally, the one I love to talk about was the lunar module, which was pretty much the ugliest spacecraft anybody had ever seen. It didn't look like it could fly, but it flew beautifully in a weightless and airless environment. And they used that to set down on the moon, and it was a magnificent machine, and especially difficult to build because you couldn't test it here on Earth. They had to build a vehicle that you wouldn't even know it would work until you flew it in space. So all of those are significant technologies that had to be brought to the fore to achieve the moon landing. But let me just suggest one more thing, and that is the structure that managed this process. All of these technological achievements had to be very tightly controlled. And so NASA put in place a very strict project management process to achieve it all so that it would all fit together and it would work as advertised. And that was a great accomplishment, which we've used many times since then, and which the international partners on the space station have used to put together that vehicle and fly it today. There's really some interesting stories about technological push. All of space technology is about doing things that have not been done before. So you have to build this new technology. But there's always things that you can use that technology for that were not envisioned at the time. I'll just use a couple of examples. So you wanted to be able to understand the biomedical readings that the astronauts had while they were flying. We didn't really have that capability in the 1950s and into the early 1960s, but NASA was able to develop what they call biobelts. They were harnesses with sensors on them that would radio back to Earth the vital signs of the astronaut in orbit, the heartbeat, the pulse, all of these various sorts of things, how much oxygen they were taking in. And they were able to monitor those. Anybody who's ever had any sort of serious ailment will be familiar with these, because they tend to get put on people today in the hospital and after they're released from the hospital so that they can be monitored, especially people with heart conditions. And it has proliferated and saved millions of lives since that time, and we use it worldwide. A second technology that I think is fascinating that we don't think about very much. We have this ubiquitous capability to communicate, to use the internet, to have computing power in our smartphones that were unheard of in this particular time. But at some level, the origins of that technological revolution were seated in the Apollo program and the other space activities of the 1960s. When NASA pursued the moon landings, they had to have a guidance computer that was small enough to fit in the spacecraft. And so it had to be, smaller than a bread box, and it had a certain capability. And by our standards, it was almost nothing. But in order to accomplish that, the Draper Lab at MIT brought together about 500 of the best engineers that they could find to work on this problem, to build this technology. And they did it, and it worked beautifully. And when the moon landings were over, that contract ended at the Draper Labs, and the 500 or so people that were working there dispersed. And they went everywhere. They went to industry, they went to universities, they went to think tanks, and taking with them the knowledge they had gained from this process and their Rolodexes, their contact list of people that they had worked with. And they seeded the microelectronics revolution and the industry that really led to that revolution in the 1970s. The space program has really a lot of very fundamental results that are really important, but one of those is global instantaneous telecommunications. We think nothing about making a call around the world to whomsoever we wish. We think nothing about going online and finding some piece of information in some disparate part of the world about anything you can imagine. That technology, that capability is really the result of our ability to fly in space. We have a satellite system in orbit, actually several systems, that are providing this global instantaneous telecommunications, which did not exist. It was so exciting when the first satellite in the early 1960s that could relay television signals broadcast the 1964 Olympics. And we could watch it live for the first time ever. Now we think nothing of this. This is how our world has changed. And while we might be upset occasionally about this modern technology and what it doesn't do for us, or sometimes it's a little overbearing and we don't want to deal with it anymore and turn off our Twitter account, the reality is that this is a result of our ability to fly in space and to use it for purposes here on Earth, and we don't want to go back, that's for sure. It's an interesting kind of relationship between those who wanted to fly in space in the pre-World War II era. And they did. They dreamed of going to the moon and going to Mars and doing all of these sorts of things. No question about that. This was a very positive sort of thing. But the money to make it possible to do those things really came from militaries around the world who invested in rocket technology. And this was true of every country that was a combatant in World War II. There were rockets that were developed in every place. The most successful of those, the one that we're all familiar with, is the German V-2 rocket, the first ballistic missile, one that could deliver a warhead of about 2,000 pounds to a target some 500 miles away. And Werner von Braun and the German rocket team was the team behind that particular technology, and it was built for purely military purposes, no question about that. In the aftermath of World War II, the Americans, the Russians, other nations of the world also engaged in this, first and foremost for military purposes. But the interesting thing about rocket technology is it doesn't care what you use it for. You can use it to kill people and break things. And that's what ballistic missiles are all about, and it created a war of terror in the context of the Cold War environment in which we believed, rightly I might add, that we could annihilate the human race at any point if we just chose to push the buttons. Fortunately, we never did. But it can also be used for creative and useful purposes, and flying in space, exploring exploring the cosmos, putting application satellites in orbit to aid us with communications, navigation, you name it. All of that is a part of that heritage of ballistic missile technology first developed for military purposes. Well, I think one of the really important challenges, I don't know if it's the most important one short term, but if we're going to become a multiplanetary species, which is the objective that most people in the space community envision, that we will ultimately go to the moon to stay and go to Mars and create a base there as well. If we do those things, I mean, they're eminently doable. All it takes is determination and resources, and it can be accomplished, although there's a lot of challenges that have to be overcome in the process. But we have it fully within our capability to do it if we choose to. The biggest issue, though, we can put, I'll use the moon as an example. We could put a research station on the moon, and it might look a lot like Antarctica, like the South Pole sites. We can cycle people in and out, scientists and technicians who are doing the work of understanding more about the moon. That would be a very useful thing to do, and it is completely within our power. But at the point that you stop cycling people and you have families that go with the intention they're going to live there for the rest of their lives and ultimately become a multiplanetary species, a big challenge is going to be biomedical. Our bodies, and indeed every living creature on this planet, was evolved to operate at 1 gravity, 1g. And so in that environment, now moving to a 1/6 g on the moon, what would a baby born on the moon be like? How would they be different from a baby born on Earth? That's a very real question we do not know the answer to. Clearly, their muscle system will be a bit different. Their bone system might be different because of the gravity being different. But we have no idea. So I would contend that and that's just the beginning of a whole series of other issues that are biological in terms of what might happen with long duration missions. We have learned that within a very short period of time, astronauts feel the effects of a microgravity environment. And recent experiments with the Shepard brothers, who one flew in space for a year, there were fundamental changes to his body over that period of time. And we have to wrestle with that as we move forward. And we can do that as long as the times in space are not so long that they're not living there indefinitely and are not born there. But beyond that, what's going to be the answer? I think that's a real challenge for the future. It is fair enough to say that we have many problems here on Earth that deserve to be attended to. There's no question about that. But let me just suggest one thing. First, every dollar spent on space exploration is spent here on Earth and not someplace else. So it goes into the economy, wherever that might be, and it is turned over multiple times. The return on investment that economic studies have found is more than 7 to 1. For every dollar you spend, you get $7 inserted into the economy through the process of multiplication. So that's a good thing. That doesn't mean that we can't address these other problems as well, and we should. And there may be some very significant pieces of this that we can learn from our efforts to fly in space as well. We can apply the knowledge that we have gained from managing complex efforts in space to dealing with down-to-earth problems. And this is especially true in cities where transportation systems, those of us who are familiar with something like Washington D.C. or pretty much any other major city knows how difficult those issues are and how we get upset when we're stuck in a traffic jam. Those can be resolved. And we have the technical capabilities, some of which are emanating from our knowledge gained in space exploration to apply those here on Earth as well.